Hello everyone. Welcome to my presentation. So today I'm going to present my paper assessing the quality of differentially private synthetic data for intrusion detection. And my name is MD Ali Reza. Amin. I am from Old Dominion University, Norfolk, Virginia. So let's get started. Data-driven techniques are central to networking and system research. This approach allows network operator and system designers to explore design choices driven by empirical needs and enable new data-driven management decisions. However, in practice, the benefits of data-driven research are restricted to those who process data, even when collaborating stakeholders have plenty to gain. So they are very reluctant to share dataset for fear of revealing business secrets and/or violating the user privacy. So we need a method to incentivize data sharing by enabling a generic framework for sharing synthetic dataset with minimal expert knowledge. So with the data, what we can actually do, we can do like a lot of things, like the structural characterization, predictive modeling, algorithm evaluation. So the structural characterization, many system designers also need to understand temporal or geographic trends in systems. That is to understand the shortcomings in existing systems and explore remedial solutions. In this case, generated data should preserve trends and distributions well enough to reveal such structural insights. And in predictive modeling, a second use case is to learn predictive models, especially for tasks like resource allocation. And in algorithm evaluation, the design of resource allocation algorithm for cluster scheduling or maybe transport protocol design often needs workload data to tune control parameters. So a key property for generated data is that if algorithm A performs better than algorithm B on the real data, the same should hold on the generated data. While there are many scenarios for data sharing, so we consider two illustrative examples here. So the collaboration across stakeholders. So consider a network operator collaborating with an equipment vendor to design custom optimization. So enterprises often impose restriction on data access between their own divisions and or with external vendors due to privacy concerns. And the second one is reproducible. So open research, many research proposals rely on dataset to test and develop ideas. So that's why actually we need synthetic data so that we can share the data and we can do research on the shared dataset. So how we can generate synthetic data? So we can use generative adversarial network, which is in short term GAN, which are algorithm architectures that use two neural networks pitting one against other. So in order to generate new synthetic instances of data that can pass for real data. And they're used widely in like image generation, video generation, and voice generation. So as you can see from here, we are showing a couple of beautiful faces here. But if I ask you, is these faces are real? What you would say? So the answer is actually no. So those are fabricated, those are generated faces, and these people, these faces doesn't exist on Earth. So how we generated this face? So we use this GAN and we trained our GAN model using some faces. This is the real faces. Then the GAN basically learned the correlation between these faces, then it generated these faces. So the main benefit, it does not require no human intervention here. So, and it does not require no human expertise in this process. So it can support different and diverse data set, and it can learn the characteristics of data automatically. So let's give some background of GAN. So there are two models in the GAN, the generator model and the discriminator model. So which basically train together. So the generator basically generates a batch of samples, and these along with the real examples from the domain are provided to the discriminator and classified as real or fake. And the discriminator is then updated to get better at discriminating real and fake samples in the next round. And importantly, the generator is updated based on how well the generated samples fool the discriminator. So in this way, the two models are competing against each other, and they're adversarial in the game theory sense and are playing a zero-sum game. So in this case, the zero-sum means that when the discriminator successfully identifies real and fake samples, it is rewarded, or maybe no change is needed to the model parameters, whereas the generator is penalized with large updates to model parameters. And alternatively, when the generator fools the discriminator, it is rewarded or no change is needed to the model parameters, but the discriminator is penalized and its model parameters are updated. So at a limit, the generator generates perfect replicas from the input domain every time, and the discriminator cannot tell the difference and predicts unsure in every case. So this is just an example of idealized case, and we do not need to get to this point to arrive at a usual generator model. So here comes the question. So leveraging GAN, are we certain that privacy is preserving in the synthetic dataset? I mean, we are generating synthetic datasets, so our concern is we are keeping the privacy very low. So the answer is actually no. The privacy, the GAN cannot promise the privacy. Here actually we cannot keep the privacy in a satisfactory level. So what do we do? So here comes another concept which is called differential privacy. So differential privacy is a system for publicly sharing information about a dataset by describing the patterns of groups within the dataset while withholding information about individual in the dataset. So differential privacy is not an algorithm. It's a system or framework described for better data privacy. And this technique is developed by Cynthia Dwork, and it is and she presented this work on this paper, Differential Privacy Survey of Results. If you interested, people can go there and learn more about the differential privacy. Let's say, let me give you a very simple example. Let's say, suppose we want to know the average amount of money an individual holds in his or her pocket to be able to buy an online course. Now, chances are many might not want to give out the exact amount. So what do we do? So this is where differential privacy comes in. Instead of asking the exact amount, we ask the individual to add any random values in the range maybe -100 to +100, +100 to the amount they hold in their pockets, and give us just the result of sum it. That is, if X had $30 in his or her pocket, by adding a random number, say -10 to it, so 30 plus -10, they give us just the result, which is $20 in this case. Thus, basically, we are not getting the exact actual information, but we are getting the information close to the original information. So yeah, that is basically we are preserving the individual privacy. So in the differential privacy, there is another parameter which is called the privacy budget. So someone designing a differential privacy system sets an upper limit on the amount of difference anyone's participation can make. So that's the privacy budget. So the system will allow someone to ask one question that uses the whole privacy budget, or a series of questions whose total impact is no more than one question. So if you think of a privacy budget in terms of money, maybe your privacy budget is $1, and you could ask a single $1 question if you'd like, but you could ask any more question after that, or you could ask like 30-cent question, then 7-10-cent question. So that is the privacy budget parameter. And Google, Apple, they are doing research on differential privacy, how to improve, how we can achieve highest level of privacy in terms of user privacy. So they are doing this research from very beginning. So here comes, there are two types of differential privacy, like the global differential privacy and the local differential privacy. So in case of global differential privacy, noise is added to the outputs of the database. That is, noise is added only once at the end of the process before sharing it with the third party. So noise is added by the data curator or the central aggregator to the output of a query of the database. So doing this, the data curator protects user privacy from people who are querying the database, right? So the data curator of the database owner is trustworthy. The database has all the private data and data curator has access to the real raw data. But each user has to trust the data curator enough to share data with it. That might be difficult. The aggregator can be untrusted company or government. Also, with the global model, all the data is collected in one place, so it increases the risk of catastrophic failure. For example, if the aggregator gets hacked and leaks all the data, so it's all gone. So then what do we do? So then we can use local differential privacy. So the local differential privacy here, you see from this image, like here this data generator or the owner will sit here. So they will generate the data here, and then the noise will be added on those data. Then those data will be stored in a database, and whichever third party users, whoever making the query to the database, so they will get the noisy data. So here, the untrusted, we don't need to trust this curator because the data is already noisy data. So here actually the privacy is already being protected. So if this curator is being hacked, so we have nothing to lose because we don't here we are not possessing the real data. So that is the experimental flow diagram. So in the training phase, we actually use the GAN and the differential privacy generative adversarial network based model to train on the real data samples. Then actually we generate the synthetic data using the GAN and also the DP GAN. Then we used supervised machine learning models which are trained on the real data samples to record the binary classification, like which is malicious traffic and which is benign traffic. Then we use the same set of ML models to record the performance on the GAN and DP GAN to compare the results. Then we also evaluate the membership inference attacks, which are evaluated on both GAN and DP GAN models. So this is the basic recurrent network neural network architecture. So a recurrent neural network is a type of artificial neural network which uses sequential data or time series data, and these deep learning algorithms are commonly used for ordinal or temporal problems such as language translation, natural language processing, speech recognition, image captioning, etc. So like the feed forward and the convolutional neural network, recurrent neural network utilize the training data to learn. So they're distinguished by their memory as they take information from prior inputs to influence the current input and output. While traditional deep neural network assume that the inputs and outputs are independent of each other, and the outputs of recurrent neural networks depend on the prior elements within the sequence. And the long short-term memory, this is the basic architecture of long short-term memory, and this LSTM is a kind of recurrent neural network. So in RNN, output from the last step is fed as input in the current step. So it tackled the problem of long-term dependencies of RNN, in which the RNN cannot predict the what is stored in the long-term memory, but it can give more accurate prediction from the recent information. So as the gap length increases, the RNN does not give an efficient performance. So that's why we use the long short-term memory here. And this is our training generator phase using the GAN. So however, we empirically find that RNN generators still struggle to capture temporal correlation when the length exceeds a few hundred epochs. So the reason is that for a long time, our time series RNN take too many passes to generate the entire sample. The more passes taken, the more temporal correlation RNN tends to forget. So to reduce the number of RNN passes, we propose to use a simple but yet effective idea called the batch generation. So at each pass of the RNN, instead of generating one record, it generates S records. So basically S is a tunable parameter, and this effectively reduces the total number of RNN passes by a factor. So as S gets larger, the difficulty of synthesizing a batch of record at a single RNN pass is also increases. So this includes a natural trade-off between the number of RNN passes and a single pass, which is very difficult to get. So this is the framework how basically we process our data set. We need to for machine learning problem, we need to pre-process our data set. So here basically there are two sets of data set we used. Here the metadata basically in the metadata, the data feature and data attribute represents a list of objects indicating the dimension, type, normalization of each feature and attribute. And in these measurements, the data feature in the measurement basically represent the value of different features in num_3 array format. And the data attribute in the measurements are basically one hot encoding of 4 categorical features. And data generation flag represents the time series activation. Check whether there is a value for that specific time or not. And here our results. The first results, like the accuracy comparison, original versus synthetic data. As you can see, this is our testing accuracy on the original data and the testing accuracy on the GAN data. And you see all they're doing really better on the synthetic data set. Some of them are very close, and here actually you see from the Gaussian naive Bayes. So here basically the testing accuracy on generated synthetic datasets is higher than original dataset, as GAN generates balanced dataset. So the size of normal data points is too large to compare with the abnormal attack data, which creates a data imbalance problem during the training of GAN. So therefore, GAN is promising deep learning tool with the capability of learning the distribution of provided data and generates new similar samples. Here, the trend comparison for different privacy budget values. Here actually I provided the result for only the random forest algorithm. As you can see, this is the epsilon values. So when the epsilon values is greater, when it is very large, the accuracy is also good. As soon as the value is decreasing, that means we are pushing more privacy, the accuracy is decreasing, as you can see. So the optimal epsilon 1 is typically considered a reasonable operating point. So we need to get 1. So if we want to get epsilon value 1, then the accuracy will decrease. So we need to make the trade-off. So here we found that when the epsilon value is 6.73, we found a very reasonable accuracy in terms of the original accuracy. And this is the accuracy comparison on the original dataset and the synthetic dataset when the GAN value, the privacy parameter value is 6.73. And then lastly, we actually did the membership inference attack evaluation. So, a good machine learning model is one that not only classified its training data, but generalized its capabilities to example it hasn't seen before. So the membership inference attack take advantage of this property to discover and reconstruct the examples used in to train the machine learning model. So this could have privacy ramification for the people whose data records were used to train the model. As you can see, as soon as the number of training sample increased, the attack success rate actually decreased. So this is our DP-GAN graph, and this is our GAN. So as you can see, there is a big difference here. When we use the differentially private generative adversarial network, the attack success rate is also less than when we use the generative adversarial network. So this is our findings, and so this is it. And thank you all for attending my presentation. If you have any question, I would love to answer.
Hello everyone, myself Sanjeev Shukla from Indian Institute of Technology, Roorkee, is going to present this paper titled Forensic Analysis and Detection of Spoofing Based Email Attack Using Memory Forensics and Machine Learning. So just going through the contents that will be covered, cover some motivation and objective of the problem, introduction, brief introduction, we'll discuss detailed proposed work, results and discussion, we'll conclude, and then talk also about the future work. Motivation. A survey was conducted by IDG Group, which also published its article online titled Top Cybersecurity Facts, Figures and Statistics, which clearly suggested that email applications are still mostly used and preferred for cyber attacks and malicious propagation, and this was found in 94% of cases. Similarly, in ABWG, also in December 2001, report suggested that they had highest number of spoofing and phishing attack. What these survey indicates is provide a motivation and the relevance of this problem in the current cyber world. Regarding objective, the objective is to detect spoofing based email attacks. We would also like to have an early warning mechanism with alerts to system admins or the security team of the organization so that they can take mitigation steps. The attack will also cover both inbound and outbound types of attack, which basically means is inbound is the received emails that has been received which try to either spoof or do phishing activity, and similarly the outbound attacks are replied emails. Now there can always be a malicious insider who can perform some kind of cyber attack and bring bad repute to the organization or the company. So both forms of these attacks are taken care of, and we achieve this through email header analysis. Going through the introduction of email spoofing. Email spoofing is basically a creation of a forced email which appears to come from an authentic source, which it actually is not, which basically means a person is trying to send an email to the user pretending to be someone which he is not. And this problem generally is because of the SMTP protocol that has been used in emails, which doesn't have any authentication mechanism. So then we'll be looking at the choices of capturing technique, because there are many types of techniques which are applied for capturing the headers, and then we'll also look for process or memory dump issue, how to handle it. Looking for the capturing technique, network forensics is one of them. In network forensics, the email header is captured from network traffic for analysis and detection of spoofed emails. Now here we are trying to capture the email headers either through network or memory. So this capturing through network is a little cumbersome process. This is because in large network we have very vast amount of traffic, network traffic that moves. So this is a problem. And the second is, even if you get the header, sometimes to prove that it is coming from the same person is difficult. So we can't guarantee non-repudiation. That is a problem with network forensics. Regarding memory forensics, what we do is we extract the data volatile memory of the infected device for analysis and study. This actually, the advantage is that it guarantees non-repudiation. of the user's digital footprint in physical memory, and he cannot challenge that because it's taken from his own volatile memory. So that is an advantage, and hence we'll choose memory forensics for capturing. Regarding the memory dump, this is a very classical challenge that memory dump has, and because every time you take a snapshot, which is the memory dump of, it is of the complete RAM, and because it is a complete RAM, what it does is it increases a significant amount of capturing time, storage space, consumes other system resources, and also the detection algorithm takes a lot of more time. Another problem is that it is hardware dependent, because it depends on the RAM size. As the hardware is becoming cheap and being used more oftenly, the size of RAM is increasing more from 16 GB to 32 and 64 to 128. So 128 GB of memory dump is a big size to analyze. So that's the problem with here. So what we'll do is, instead of taking a complete memory dump, what we'll do is we'll capture the process. So our approach only captures the browser process instead of capturing the complete RAM dump. What this immediately does is reduces the capturing time, storage requirements, and the utilization of system resources, and even makes the detection algorithm faster. Since the complete RAM dump is not involved in our approach, it is entirely hardware independent. Now, looking at the proposed work, so our system architecture is this way. The email is taken, email header is taken, and what we does is we capture the email header. So there are basically two big modules. One is the email header capturing module, which has all these sub-modules, and the second one is, once this has been captured, the detection algorithm, which is the spoofing email detection modules. One is for receiving emails and other is for replied emails. Once this has been decided, then finally the mail has been decided as either legitimate or spoofed, and if it is a smooth one, then an alert is sent by email to the system admins. This is the system architecture we have. Same is written here. So first we'll look at the first module, which is URL extractor module. This is the novel module which we have added. The task of this submodule is to extract the URL of a process with an open email inbox and extract features from the URL representing an email transaction. In order to perform this particular exercise, what we have done is we have studied 35 most popular email servers currently used to provide email services. Our experiment included extracting the open email URLs. For this, we had created email accounts on these servers, and that gave us access to email inbox. And after obtaining all the URLs from these email servers, we closely examined the structure of the complete URL to extract common features that can be attributed as distinguishable. Distinguishable here means that whether the URL is relevant for our purpose or not. So what in this feature extraction, as per our study, we got 8 features, F1 to F8 we have identified. Out of this, F1 to F6 are text-based features, while F7 and F8 are other features. Out of the 8, F1 to F7 are novel features, and the F8 is taken from literature. So this is the table which represents the complete list of our features from F1 to F2 to F8. These are the features we have taken: mail, message IDs, inbox, message, home directories, user IDs, special characters, and HTTP and HTTPS count. And here we have applied search and applied them. Regarding dataset, our dataset comprises a total of 33,080 URLs, of which 14,350 URLs are downloaded from the 35 popular email servers having email features, and the rest are non-email URLs that we have used from Alexa top website. So these two we have mixed it. We have mixed the URLs from email and non-email. We have mixed it. We then prepare a CSV file that has 8 columns representing the 8 features and the tuples representing the URL. What we do is we take each tuple, we search the keyword, and if the keyword is present, then that keyword is marked as 1 or 0 based on their presence in URL. And in this way, we have prepared our CSV file. Now, the first thing we do is for feature extraction. Feature selection is the most critical part of any ML data model. So here we have used filtering method. To achieve this, we have used filtering method. What we have done is we have first tried chi-square test and information technique. We have tried these two, and what we have found that is chi-square results were not appropriate for our problem statement, as it is dependent on significant level. Therefore, we have chosen IG, which was more appropriate in terms of results for our problem. As we can see from the figure on the right side, the ranking of all the features based on the info gain values are represented in X and Y axis, and as we observe from this, the gain value stagnates at F6, F7 and F4, and then takes a dip after F8. So thus we select the top 7 features which have the highest significant value and impact on the model. Next is the classifier selection. Here we have taken 6 binary classifiers, and we test we have taken and we test this with the 7 features that we have selected. All the chosen classifier performances evaluated based on precision recall and F1. So here's the performance comparison of the classifiers. Based on them, we choose the RF classifier based on their performance. What we can see from this is that this one, RF, has best performance. It also avoids overfitting, while model build-up time is marginally higher, 1 or 2% than DT. So we have chosen RF as the classifier. Regarding other modules, memory forensics is the live active process from memory associated with email are captured using PID. PID obtained from URL extraction module. We then extract the string, the captured memory dump. We extract ASCII and Unicode strings, and then we filter email header field that the detection algorithm we use in extracted from the string file. So this completes our first capturing module, and then we come down to our second module, which is detection algorithm. Some of the header fields that have been used for a detection purpose is tabulated here. We use from to message ID, SPF, TCAM, DMARC, ERC reference, and MX record fields for our detection algorithm. So detection algorithm for received email, first we'll look at that. So this, we extract SPF, DCAM, KM, ARC header and analyze the values of each field as per algorithm 1 and determine whether an email is spoofed or legitimate. In case of legacy email servers, we have legacy email servers are those which have not implemented SPF, DMARC or a TKM kind of authentication protocols. So even in that case also has been taken care, and what we have done is we rely on message ID based spoofing technique. For detection algorithm for replied email, what we have done is that we try to match the header values of references and 2 fields. If they match, we declare it as a legitimate email, else we again check it by querying the DNS through forward NS lookup to fetch MX records. So the domain names thus obtained is matched with reference fields, and in case of a match we consider it as a genuine email, else we declare it as a spoofed email. So what we have also done is a local database of MX record is maintained in order to increase the algorithm speed and also to reduce the bottleneck and dependencies on internet connectivity. We found that at some places where there is poor internet connectivity, we had challenges. The algorithm first queries the local database and then queries the DNS, and also saves this value to keep the database updated. So this way we keep we take care of poor internet connectivity issues as well and speed up our algorithm as well. We take an example in order to show how this works. Here what we see is there's a to field, and this is a genuine email, yet if we match it with the reference field, this shows it says spoofed email. So what we do is, it has been experimentally tested and identified that reference matching fails when enterprise purchase email related services from email vendor. So this has been found. For instance, for example, if we take there's an enterprise called IIM Raipur which uses the G Suite from Google. It has purchased. The email will retain the original domain, that is iamraipur.ac.in, but the reference generated by MTAs of the original email server here Gmail has the Gmail domain. Now what this does is, whenever we compare the to field domain with, always show a legitimate email as spoofed, because reference field shows gmail.com whereas the domain is iamraipur.ac.in. Raipur. So if we match it, it's always fails. So what we do is the shortcoming is resolved by MX record. We query the query the DNS, get the MX record and see it is a Google, get the results, and then we match this MX record with a reference field, and this is a match, and then we can declare it as genuine email. So in experiment and testing, what we've done, our program runs as a listener event to check the browser instance to call back and activate the URL extraction function. Now each instance of a browser execution triggers the event listener of the URL extraction module to obtain the URL and PID, which is the process ID of the browser tab, and verify whether the URL is of relevance. Email is opened in the browser or not. The relevance of URL is found by applying a machine learning, which uses the 7 email features, URL features as explained above. If the URL is not relevant, it is immediately rejected and the program stops. The output of the URL extraction passes the PID to the process capturing tool, which generates memory snapshot files of the process associated with PID. This file is used to finally extract the email header. Further, the header field values are then extracted and saved to create a CSV file. And this finally CSV file is used to implement the spoofing detection algorithm. Results and discussion. Just go ahead. Excuse me. The result of URL extractor is shown here. We have chosen the random forest classifier has been identified. An average value of 98 is obtained. The result for detection algorithm is obtained here. The proposed method has got these results in terms of accuracy, precision, recall, and F1 score. And we have also compared with the other past approaches how they have achieved this. Performance analysis. Performance analysis was done by taking into consideration the system resource utilization, processing overheads, and time analysis to judge how better our methodology worked. Average values of CPU utilization, memory usage, and disk utilization was observed along with time taken during execution of program, and those have been tabulated here for each part, each process we have done. We have also compared about this performance with other past techniques. A total time that required by the proposed method, which we have proposed for capturing live process dump to detecting spoofed email, is 35 seconds approx, which is quite fast. This is better than the 12 minutes time taken for the performance analysis by a similar method, which you can see reference number 10. This is, and the 1 minute time taken by the process based approach 11. These are the two we have taken for comparison, because of the one has achieved 12 minutes time and other has achieved 1 minute time, and PM here is the proposed method. So this is we have compared and shown that our method has performed better. Similarly, we are also compared the detection time versus the different sizes of captured data file, and we can see the detection time required for varying size of captured file shown. These are the memory dump captured with live memory, and the average detection time is approximately 34.5 seconds for an average data file of 161. We have compared out here. Comparison point, if we talk about, we have recognized and defined the comparative checklist issues, and we found that our proposed method was compared with these from other relevant studies with the help of a benchmark checklist as shown there. The results has been shown. The results have got the scores between 16.6 to 83.33, covering 1 to 8 benchmark points, and these scores have been mentioned out here. The comparison score also validates our comparison analysis with 10 and 11, as both of them are the top two highest scorers. We can see here this is the 10 which got 66.6, whereas 11 has got 83.3. These were the scores. So these were the top two performers. That's why we had used them to compare with our previous studies. Commercial application and limitation. The proposed method can be deployed as a client-side solution that can detect email spoofing. The novelty of memory forensics is that the organization can even prevent email spoofing in scenarios where it does not owe the email server used by the employee in the organization. What this means is that there are scenarios where the small organization doesn't have their email server. They too can apply it, use this. And the schema can detect email spoofing even when the emails is received in a personal email service used by employees on the host provided by the organization. So it can detect there also. The limitation of proposed scheme is that it currently tested on webmail based email services only. So finally, coming to the conclusion, we can see that this is memory forensics provides guaranteed non-repudiation. We use the exact process to has been captured instead of taking memory dump or all the browser processes. Our work of taking URL model extractor module is novel, and an alert mechanism of emailing the log files is also been included, which has been sent to the system team. And our performance shows that the proposed work takes approximately 35 seconds. So this is the conclusion. Future work is that we can extend and include the email client applications like Outlook and Thunderbird, etc. The proposed thing can be extended to mobile phones also to test this performance and efficacy on Android and Apple OS. Thank you.
Hello everybody, my name is Yuedong. I'm a student from Institute of Information Engineering, Chinese Academy of Sciences. Here I'm going to present our work called AttackMiner, a graph neural network based attack for attack detection from audit logs. The goal of general attack detection is to find a set of behaviors related to the analysis. When a security analyst wants to determine whether an attack has occurred inside the system, he usually needs to conduct a lengthy and complex search and analysis of massive logs. This makes attacks difficult to detect. Typical attack detection methods can be divided into two types. One is the traditional method, that is the method of non-provenance graph, such as log length. The other is method based on provenance graphs. This method use various graph processing techniques to detect attacks such as rapid. Recent studies have shown that the provenance graph-based approach has many advantages. However, relying on long-term logs to build a complete provenance graph has significant processing and storage overhead. In practice, there are already multiple frameworks that divide attacks into several stages, such as Lockheed Martin, CyberQchain, Metro, ATT, and CK. So we think, can we focus on key steps of attack activities? Now, let's see a motivating example of our paper. In this figure, the shaded area representing a key attack behavior. This attack mainly starts by exploiting the vulnerability of NGX. The attacker downloads and executes the malicious temp file, triggering an alert for file execution. The attacker then writes to another log file, communicates with the malicious server, and even attempts to inject into the SSD process. Likewise, as long as attacks exploit the vulnerability of software to invade the system, even if the system is running a different background task, the attack behavior in this figure can be achieved. Okay. Our key idea is that we treat the attack detection task as a graph classification problem and consider the various contexts of attack behavior. We design a GAN-based model to aggregate graph information. Our approach has three advantages. First, no need to search through massive logs. Second, efficiently process graph data by GN. Third, no additional expert knowledge about attacks and target system is needed. Now, let's look at AttackMiner. It mainly consists of four parts: dynamic log sliding window selection, provenance graph construction and optimization, deep learning model based on GN, and attack detection. Next, we introduce our log window sliding mechanism. The two adjacent log windows are not completely separated. This is to cover various situations as much as possible. After each move is completed, AttackMiner constructs the provenance graph with the log events in the current window. The distance that the window moves each time is a random time that varies according to the probability. We use uniform distribution in our work. Since the last time the provenance graph was constructed, the longer the sliding distance, the greater the probability of stopping to build the provenance graph. Additionally, in order to gather useful information, we suggest choosing log windows with an appropriate length based on the target behavior. AttackMiner mainly uses three techniques for graph structure optimization. First, AttackMiner eliminates isolated nodes in the provenance graph since these nodes don't have even enough graph structure information. At the same time, we merge socket nodes with the same IP address connected to the same process. We don't differentiate whether a pod is malicious or not, in order to obtain a compact provenance graph. Second, we remove redundant edges while preserving semantics. In this figure, before a read at time T3 occurs, the write event at T2 is repeated, with the write event at T1. So the write event at T2 can be removed. The write at T4 occurs after the read at T3, which affects process 1. So it should be returned. Third, we further merge nodes. AttackMiner merges nodes and their edges whose incoming and outgoing edges are events of the same type. As shown in the right figure, nodes file 1, file 2, and file 3 are merged into one node file 1. because these share same types of incoming edges and outgoing edges. Attack provenance graph construction is a key step. The aim is to use various log contexts as the background and construct an attack samples with rich background and information. This figure depicted an example of attack migration. GB represents a benign province graph. The right half of the finger, GA, is an attack subgraph extracted from attack campaigns. The attack in GA invades the systems through the vulnerability of the index and the seeded index node N1 is the intrusion point from malicious behavior. In the benign provenance graph GB, we found the target process node with the same type and name as the intrusion point. An index node N2 marked with shadow in GB. And then we migrate the events associated with node N1 to node N2. Now, we introduce the deep learning model. We use the word to vector forward embedding and choose the GAT as the basic component. GAT is implemented by stacking simple graph attention layers, which introduce a self-attention mechanism in propagation process. This is the attack migration algorithm. This algorithm mainly includes two functions: merge invading process nodes and target process nodes, migrate associated events. Finally, we get the malicious provenance graph, including attack behaviors. We try to evaluate our system using the WTC dataset. For each attack scenario, we construct the corresponding attack subgraph. We leverage attack migration to generate datasets containing benign and malicious provenance graphs. This is the effectiveness of optimization techniques. AttackMiner reduces the number of entities by an average of 80.20%, and the number of events by an average of 83.39%. The provenance graph optimization improves the overall accuracy by 14.76%, and F1 scores in all 5 categories also have improved significantly. We implement a set of cutting-edge approaches and compare their attack detection performance to that of AttackMiner. It can be seen intuitively from this graph that AttackMiner has high accuracy on all categories. Due to the use of optimized provenance graph, the SVM, random forest, and KN also have certain classification capabilities, but the effect is far less than that of GN methods. This is because GN can effectively learn the structure information of graphs. We evaluate the impact of log window size. The size varies from 30 minutes to 70 minutes. In this figure, as the log window becomes larger, the detection accuracy decreases slightly, but still maintains a high accuracy. When the log window size becomes 70 minutes, the AttackMiner detection accuracy is still above 96%. Additionally, in order to get the useful information, we suggest treating log window with an appropriate length based on the target behavior. From our experiments, the length can be set to at least 60 minutes. We encourage users to set the length to be appropriately large, but it's best to do preliminary experiments based on the target activity before setting it. Okay, let's have a recap. AttackMiner combines provenance graph analysis, neural language processing, and GN techniques. AttackMiner uses optimization and attack migration based on provenance graph structure. AttackMiner can successfully identify different attacks. For other details, please see our paper. Okay, thanks for your time. Any questions?
Good morning, everyone. This is Mohan. I'm going to present our work on Hiatus unsupervised generative approach for detection of DOS and DDoS attacks. This work was carried out by our research team, which is comprised of Sivanand, Vinay, Rajendra, Hongyi, Mingcheng, and myself. As you all know, network attacks pose a serious threat to the growing internet traffic. And such attacks could compromise the integrity, availability, and confidentiality of the network. DOS, which refers to denial of service, in which case a target resource is flooded with large amount of requests such that the system becomes overloaded and could not handle legitimate requests. DDoS is a related one, but the difference is that the traffic flooding happens from the sources which are distributed. In other words, there are different sources which generate or which flood the traffic towards the target. The following figures show or illustrate DOS and DDoS. So motivation of our work we can see that DDoS attacks focus at different benefits, which could be financial or economic benefits, or it could be used for political, military advantages, and there could be other reasons as well. According to Kaspersky reports for Q2 2020, number of DDoS attacks increased threefolds in comparison to Q2 2019. And also 94.7% of the attacks are SYN flood attacks and about 5% are ICMP attacks. As you can see, we present three figures. One on the left hand side shows the number of DDoS attacks for various quarters in 2019 and 2020. And the second figure shows the distribution of DDoS attacks by country. And the third one shows the distribution of attacks by the different types, whether it is sync attack, ICMP attacks, etc. So there are different related works which also work on detecting anomalies, okay, or consider the DOS and DDoS attacks. And these are some of the key related works which are tabulated here. And in the interest of time, I'm not going into very specific details of everything, but we can see that the different works and the references are given in the first column. And the next column shows the type, whether it's supervised or unsupervised or semi-supervised. And third column shows the techniques used by such works. And the fourth column presents the data sets used to experiment or evaluate their work. And finally, the drawbacks or limitations of them are illustrated here. So what is the gap which we are trying to address here? Okay. So if you look at supervised learning based approaches, they require label data in huge amount, which also requires high computational cost and time. And there is another important limitation of the existing works, particularly the machine learning algorithms like decision tree, random forest, k-means, etc., is the curse of dimensionality, which require dimensionality reduction and special domain knowledge. Okay. And another important point to note is that several works use old or outdated datasets. And if you notice KDD CUP 99 NSL KDD datasets, such datasets do not contain the recent or latest DDoS attack types. And also, the deep learning based models involve high number of trainable parameters, and when deep learning models are ensembled, the inference time increases. If you look at the clustering algorithms, they all have their own disadvantages. For example, DBScan fails with clusters of similar density. And if you look at the semi-supervised clustering, noise in the label data used for predefined clusters could lead to bad clusters. So these are all some of the limitations of the existing approaches, okay, which we try to address and avoid in our work. So if you look at our problem, basically we develop DDoS detection system capable of detecting DDoS attacks from network traffic without relying much on label data in an unsupervised fashion. And another capability which we are targeting is to handle high dimensional data and to generate abstract features from high dimensional data without involving domain expertise. So we are trying to address in our problem, which we are exploring, okay, addressing the limitations of existing approaches. And these are our contributions. We propose a system to detect DDoS attacks. Okay. Basically, we use generative adversarial network, GAN, and variational autoencoder VAE, trained in an unsupervised fashion, which could be used to develop the system to detect DOS and DDoS attacks. We train models on the dataset CICD DOS 2019, consisting of modern reflection-based and exploitation-based DDoS attacks. To validate the performance of the proposed techniques and benchmarking, we also train and test our models with other datasets like UNSW and B15 dataset and CICADS 2017 dataset. When we look at the generating models, GAN and VAE, they have some attractive features. They eliminate the reliance of label data to a large extent, and they could be trained on a single category of data, benign or malicious category. And we know that collecting one category of data without contamination is not feasible. So VAE is trained with one category of data with few records from other category as outliers. Hence, our model is shown to be robust to outliers in the training data. An advantage of generating models is that they learn the distribution of the training data. So the additional feature selection techniques are not required, and they can avoid domain expertise and complex feature engineering procedures. So by using these generative models, we are trying to address the gaps which we mentioned before. Okay, the key principle of GAN is something like this. GAN consists of a generator network, G, and discriminator network D trained in adversarial fashion. Generator G learns a distribution P over the input data through the mapping G of Z. Discriminator D maps the input data to a scalar value, either it's real or fake. Both D and G are simultaneously optimized through the equation given below. The anomaly score is calculated based on what is called residual loss and feature matching loss through a threshold. Residual loss measures the visual dissimilarity between query data X and generated data, which can be given as the following equation: LR equal to absolute X minus G of Z. And the discriminator loss, as far as discriminator loss, intermediate feature representation of discriminator is used. Okay. For example, LD equal to absolute f of x minus f of g of z, where f is the intermediate feature representation. Okay. And the figure shows the basic framework of GAN with the generated discriminator, okay, and the data X and the intermediate F and the output, which is yes or no, that is the data is real or not. Sorry. Variational autoencoder, a structure of VAE is similar to AE, that is autoencoder, which basically has three components: encoder, latent variable, and decoder. VAE is a probabilistic model with capability to produce new samples. Encoder maps the input to the latent variable Z, which is a normal distribution. Decoder samples the normal distribution and generates new samples. During the training, the parameters of normal distribution, mean, standard deviation is modeled basically. So you can see here, so there are few components. So first one basically Q Z given X, then P of X given Z. Okay? And I think those who are interested to know more can refer the reference below. And or the relevant literature. To continue further on VAE, the objective function of VAE is the variational lower bound of the marginal likelihood of data which is given by this equation. The first term is KL divergence between approximate posterior and a pair of latent variable z. Then P theta x bar y, x given z is the reconstruction likelihood of data given latent variable z. Monte Carlo estimate of the second term of equation 1, this is the equation 1, gives the reconstruction score. The reconstruction score is compared with the threshold to classify if data is malicious or benign. As far as the performance evaluation is concerned, we consider 3 data sets. The recent one is CIC DDoS 2019, then CICIDS 2017, UNSW NB15. We carry out experiments for both our models VAE and GAN, and the key performance metrics used are this: precision, which is given by TP by TP plus FP, then recall, then false positive rate, and F1 score, accuracy. So these are the definitions of these metrics. So in interest of time, I skip these definitions. Those who are interested can refer the book to understand better. ROC, we plot ROC, which basically is receiver operating characteristic, which is nothing but the graph TPR versus FPR. So TPR stands for true positive rate, FPR stands for false positive rate. AU ROC represents the area under ROC curve. AUPRC refers to area under precision recall curve. And to go further on the results on the first data set CICDD DOS 2019, it contains reflection and exploitation based attacks captured on 2 days. 65 features are used, and it consists of 13 different attacks, so which are listed here. And we use around 60,000 benign records. GAN and VAE are trained primarily with DDoS records. And for the data set CICD 2017, this is how we collect the data. The flows obtained through CIC flow meter for a total of 5 days. It includes various attacks like brute force, DDoS, bot infiltration, etc. Both the benign and DDoS records are used. 64 features are used, and this shows the number of DDoS and benign records which are sampled. And GAN and VAE are trained primarily with DDoS records. Similarly, for the third dataset UNSW NB15, it contains traffic obtained through TCP-dump tool. It consists of 41 features. Then it consists of around 2 million benign traffic and 60,000 DOS traffic. Here, GAN and VAE are trained primarily with benign records. And this is also our experimental setup. And for different data sets, we specify the batch size, noise dimension, EPOS, and whether we train with benign data or anomaly data. So this is the experimental setup and the parameters for the experiments with VAE. And again, shows latent dimension, batch size, EPOS. Then we also specify whether it's trained with anomaly data or benign data. And the sample size is also given. And if you look at the performance results, CAC DDoS 2019, basically the figure shows the results for GAN. So you can see on this particular table, the results for DDoS benign in terms of precision, recall, F1 score are given. And we can notice that we get very high performance results, which is, let's say, 0.991, so it's close to 1. Okay. And this table below shows how it is trained. For example, the training is done with DDoS records of this size. Validation is done. For validation, how many benign records are used, DDoS records are used. Similarly, for testing, how many are used. So these details are given in the table. And on the right-hand side, you can see the ROC, which is TPR, true positive rate versus false positive rate. And you can see that the area under ROC is close to 1. And obviously, this shows good results because this is towards the left of the diagonal. This is what we desire. Similarly, if you look at the precision versus recall curve at the bottom, you can also see that the area under this is close to 1. So, and this is the points are towards the right top corner. So that means they show good performance. And for VAE, similarly, we have, with GAN, so you can see the data, so the results are presented with different percentage of training data. So obviously, when the percentage of training data increases, the performance increases. Similarly, with VAE also, we made similar observations. So the table here on the top, it shows the precision recall reference score. And on the right-hand side, we show the ROC and PRC and their area. And you can notice that when the training percentage of training increases, the performance increases. And next, we show the performance of both GAN and VAE. So for 70% training data, so you can see that both they do well, okay, and GAN is doing slightly better than VAE in terms of ROC as well as RRC. There's the blue line. And below, if you see the table below, it shows the proposed methods, the performance of the proposed methods, VAE and GAN, in terms of accuracy, TPR, FPR, and F1. And you can see that the accuracy and TPR are quite high, and the false positive rate is low. And this figure shows the results for the other data set, CACD S2017. And we also observed, similar to the previous data set, the ROC and the area under the ROC is quite good, which is close to 1. Okay, and the figure on the right hand side shows the performance for varying percentage of training data, let's say 50% to 90%. And and the table below on the left hand side shows how many data records are used for training, validation, and testing. And you can see that in general, the performance is good, except that for DDoS, the precision is not that high. But overall, in terms of ROC and PRC, they all do well. And this is the results for VAE. And for VAE, the results are quite good when compared to GAN. So you can see on the left-hand side table, the precision recall values are close to 1. And similarly, if you look at the right-hand side, ROC and RRC, so the area under this is close to 1. You can see 0.96 plus here also 0.98 and 0.99. And for the same data set, we just compare GAN and VAE, okay, for one specific ratio, 70% of training data. And you can see that both are doing well. Like GAN, we get the area under this is around 0.945, and VAE it is 0.97. Similarly, if you look at the PRC curve, the performance is also quite good for both VAE as well as GAN. Okay. And this data set, okay, being little old data set, we could compare with other works, okay, as a benchmark. So you can see on the left hand side there are several methods which are shown here, and these methods, some are supervised, some are unsupervised based approaches, and the last two rows correspond to our proposed approaches, VAE and GAN based approach. And you can see that the accuracy is quite high and false positive rate is low, and precision, recall, F1, they all we get reasonably good or high values. And you can notice that compared to the supervised approach, the performance is slightly lower in terms of some metrics. And this is expected as we try to avoid the supervised learning approach, use of label data. So obviously, supervised one is doing better in terms of some metrics, let's say accuracy, or let's say recall. So this we can understand. Then about the final or the last data set, UNSW and P15 results. And the result shows for GAN-based or proposed approach. And here also you can see that it gets the best performance possible. And on the right-hand side, if you look at the ROC and the PRC curves, the area under them is 0.99, here also 0.8, which are quite good. And finally, this slide shows the results for VAE, and the results are also quite good, similar to the GAN. Here also you can see the area under ROC as well as area under PRC, and you can see the values are quite high, like 0.8 plus. Here it varies from 0.94 to 0.8. So this slide compares both GAN and VAE for this data set for one particular case of training proportion or percentage of training data. And you can see that GAN and VAE both are doing good in terms of ROC as well as PRC. And GAN is slightly doing better than VAE. Okay. And this is the benchmark result with some of the existing works. Okay, how they compare. The last two rows are our works, and the first two are the existing works. So you can see that our proposed VAE and GAN-based approaches, they do quite well. See here, F1 score, TPR, and accuracy, they are close to 1, and the false positive rate is very low. Okay. Any questions? Thank you for listening to our presentation.